In this video we are going to see Biot Savart equation or Biot Savart law. This has to do with the magnetic field. So here we have the source of the magnetic field. So this is the source. And let's say that we want to know the magnetic field at this point. Magnetic field is represented with the letter capital B. This letter, and we have talked in other videos about the magnetic force. Here we are going to talk about the magnetic field. So experimentally it was discovered that the magnetic field is directly proportional to the charge that is producing this source. So the charge, it is also proportional to or inversely proportional to the square of the distance. Now it is not this distance. The distance that I'm calling here R is the distance that is perpendicular to the plane that the line between the source and the point P and the velocity of the particles lie. So here we have a plane. In this plane, the board is a plane. This plane is a plane in which this line, that is the, let's say, this distance between the source and this point, this line lies there. And also the velocity could be that the velocity be in this direction or this direction or wherever. But the distance here at which the magnetic field is inversely proportional to the square of that distance is a distance that is perpendicular to this plane. So it would be out of this, so it would be in this direction, because this is the normal to the plane. This is the direction. Now, so we can write it as magnetic field is equal to the constant of proportionality. That constant is mu naught divided by 4b. This is the constant of proportionality. Mu naught is in units of Henry per meter. Henry meter, I think so. So, and also remember that, and we will discuss this later, but the square of the velocity is equal to 1 divided by epsilon naught mu naught, or c is equal to the square root of this. Well, in any case, we have mu naught divided by 4 pi. This is just a number, but we like to put it in this way. Mu naught is just again a constant, a number, so we can just operate this and we will have just a number, but we like to put it this way. So anyway, the magnetic field is equal to the constant of proportionality times, we say it is proportional to the charge to the velocity, and inversely proportional to the distance. Now here we need to take, because we are talking about a perpendicular, we are going to introduce something called the R vector. R vector is, because I cannot just multiply Q times P, I actually need to take this cross product with the vector R, because if I take the cross product, I will take only the perpendicular component of the velocity, because the charge is not a vector, so I use it with the velocity. So I need to take this sign. And so this cross product is the same as the magnitude of the velocity times the magnitude of the unit vector r. This is the unit vector r, so the magnitude is just 1, but we put it this way because we want to indicate that it's perpendicular. So our r vector is defined as, or our unitary r vector is defined as a unitary vector, so the magnitude is just 1, but it is in the direction perpendicular to the plane in which this line and the velocity lie. So that is our r vector, and so this is the magnetic field. We need to take the cross product. In other way, you can put it, if you don't want to write here the unit vector, but you want to put just the distance, for example, this distance is perpendicular. Well, here would be perpendicular, so could be this line. Then you can write it as, because r caret, that is the unit vector r, you can write it as, well, it is the same as the r vector divided by the magnitude of r vector, and this would be exactly just a vector with length 1 and in the direction of r, so that is our r caret. So you can write it as the magnetic field is equal to 2 mu naught divided by 4p times the charge times the velocity cross product r, and here you put the vector notation, not the just caret, divided by r, or divided by the magnitude to the third power of the radius, because here you need to put this part here, and you put the, here is just the magnitude, so you don't care about the sign, and here whenever you have minus or plus it's going to be a square, so it doesn't care. So you need to put this sign that indicates that you're taking the magnitude. So this is the magnetic field, whatever of these two equations you want. But we know that Q, or you could say dq, whatever you want, dq is equal to whatever charge I have. Let's say that I have some number n of particles moving in a volume, so I have n number of particles moving per unit volume, and I will call this number small n. And let's say that the charge of these particles is the q. So with the charge of just one particle. So I have that this n times dq times now the volume. This is the charge that I have. Now the volume, you could also write it as area times the distance, and the distance is what small distance this cross-sectional area is advancing, so could be an infinitesimal length, so you can write it as this. So this is the q. So you have that the dB, let me do it with other color, so I have, I need to erase it. So I have that dB is equal to, would be mu naught divided by 4p times instead of putting Q or DQ, this Q I will put N Q NQ area the L, and this cross product with the radius. I like more the notation of putting a caret here, so do it with the unit vector and here the square of the radius, but you can use wherever you want. Now remember that the current that is charge per time, charge is here we have it, N Q area dl, and you will divide this by time. So yeah. Oh, and I forgot to multiply here times the velocity. Sorry, times the velocity. Times the velocity and then the cross product. So the current is this times the velocity, because area sorry, this part, because area times velocity we discussed in our first video of Gauss law for electricity. In our introduction we saw that flow is area times velocity. So this is flow, and the units of flow are cubic meters per second. Then I have N, that is the number of particles per volume per cubic meter. And then I have the charge. I will have the charge here divided by time, let's say second. So sorry, use the charge here. So first I kill this, and I just have now the number of particles times the charge. So this is this will be sorry here. The number of charges, the number of particles times Q is the number of charge that I have, that is the number of charge that I have, and then I have this divided by second, so I have this. So I have that the current is equal to NQAB, or I could say that the current is Q divided by T. You could also see it here. If you divide this Q by T, you have current. Yeah, I misplaced some T here. I hope not to have confused you. And so now here this dl, that is distance divided by time, it is velocity, and so you have nqa velocity. So the issue is that here this n a b q you can replace it by current, and so now you have that the magnetic flux, this dB is equal to mu sub naught times 4b times the current times or dot product the unit vector in the r direction divided by r square. So now B, or the magnetic field, is equal to the integral of dB, and this is equal to, this would be equal to the integral of this. And dl here, sorry, I forgot to put dl here, I dl, and so here when you now can take everything except the L out, and so you have that the magnetic field is mu sub naught divided by 4p times the current times the integral of the L cross product, the unit vector, divided by the square of the vector. And this is Biot Savart equation. In the next video we will see why the magnetic field of a circular conductor is just the famous way of saying magnetic field is equal to mu sub naught times the current divided by 2 pi